Hi everyone, this is Devi Sattam and you're watching EE635 Applied Linear Algebra, the fourth lecture. This happens to be the first module. Okay, so let us do a very quick recap of what we have done so far. We have been concerned with solving linear systems of equations so far. We saw that with real numbers, this system of linear equations can be represented as AX equal to B, where A is a known matrix of size m cross n with real entries. B is a known vector of size m, so it's a column vector of size m with real number entries, and X is the unknown. We have to solve for X. That means we have to find out an X, which is a real n-sized vector, column vector, which satisfies the equation AX equal to B. That is what we mean when we say that we have to solve for this system of linear equations. We've seen techniques of how to do that. That required us to have the idea of equivalent systems. We've seen that equivalent systems can be obtained by doing elementary row operations, which also amounts to multiplying the matrix A and the vector B by a square invertible matrix M. A sequence of these M matrices multiplied from the left to A and B finally leads to a special form of these equations, which is equivalent to the original system of equations known as the row reduced echelon form. And from there, we have found out that by looking at the row reduced echelon form equations, you can just read off the solutions immediately. And the moment you can read off the solutions, there as a byproduct, one can also figure out whether this system is solvable, that is, whether there exist any solutions, or whether there are no solutions, yeah, or whether there are infinitely many solutions, right? How many independent variables are there? How many dependent variables are there? All these things can be figured out. And not only just that, one can actually write down all solutions in a parametric form is what we have seen by investigating this row reduced echelon form matrix. And in between, as byproducts, we have also obtained several corollaries of that. Like, for example, if it's a homogeneous equation, that is, if the right hand side is 0 and number of equations is strictly less than the number of variables, then there will always be non-trivial solutions. Yeah, that was one of the prime corollaries of what we have done so far. Right? Now, in this lecture, what we'll concentrate on would be the following. We would be seeing two levels of abstraction as far as the solving linear systems of equations is concerned. Now, what do we mean by abstraction? Okay, let us try and see what the literal meaning of the word abstract comes out to be. Let me share my screen here. I hope my screen will be visible to you very soon. I have already, yeah, there you go. I have already searched for the meaning of this word abstraction, right? So what does the dictionary meaning of abstraction say? It says that the quality of dealing with ideas rather than events, or freedom from representational qualities in art. I'm sure you must have heard of abstract arts. Yeah, many of you may be connoisseurs or admirer of abstract painting. Like, for example, I will give you two such instances of abstract art. This is a famous art by a very famous painter called Mark Rothko. This happens to be one of his most famous abstract arts. This is a style that he had developed, and he actually has done several such abstract arts, which most of them, I mean, many of them actually look similar to this one. Let me show you a few more of Rothko's paintings. Here, this is another one. This is another one. Now, you see, this does not show something, it does not depict anything that you may have seen, any object that you may have seen before. Like, for example, it's not a human figure, it's not some geometric object, geometric shape that you see very often. It's very difficult to say what this really means. It may convey some idea to you, some feeling to you. That is why it's abstract, because it's not manifest. It's not something that can be represented concretely. It tries to capture a feeling. Yeah, if you remember the second definition, it says that freedom from representational qualities in art. So it tries to capture, uh, a feeling, not something, some representational, some existence, yeah, but some sort of feeling. Similar sort of things you can find in Picasso's painting also, like this one. This one is called a Weeping Woman, done in 1937 by Pablo Picasso, one of the greatest painters of all time. So this one is not just one picture of a lady crying. It's not like that. It also tries to capture the mood. When you see somebody crying, or when you cry yourself, I mean, I'm sure all of you must have had this experience at least, sometime in your life. Um, it is also the mood of, or the act of crying, the sorrow, the melancholy. That is something that perhaps this painting tries to capture. Yeah. Now, when it comes to abstraction or abstract theory in mathematics, the idea is although similar to this one, but not exactly this idea of abstract. So abstraction in maths does not mean that you try to capture some feeling or something. Yeah, it's not like some philosophical idea or some metaphysical idea, not like that. When it comes to mathematics, abstraction has a meaning which is quite similar, which is quite closely captured by this particular definition that I'm going to discuss now, this one. So it says abstraction is the process of filtering out or ignoring the characteristics of patterns that we don't need in order to concentrate on those that we do. It also it is also the filtering out of specific details. From this, we create a representation or an idea of what we are trying to solve. So abstraction in maths lets you, so in crude words, it lets you prune away unnecessary details. It filters out something that you need. And with that, it builds an idea which becomes applicable to a larger class or a larger family of things. In this lecture, we are going to see two such levels of abstraction. Yeah, in the first module, we'll discuss the first level of abstraction, and in the second module, we'll discuss the second level of abstraction. And then from that point onwards, we will concentrate our studies mostly on this abstract idea of linear algebra, and then we will see that how these abstract ideas get applied to various different practical scenarios. Okay, so let us proceed. What we are talking about here in terms of abstraction is the following. So let us ask this question then. Okay, we were trying to solve this ax equal to b problem, right? Where, as I've said before, A is a real matrix of size m cross n, B is a column vector of size m, and X is a vector in Rn, vectors of size n, and this is unknown. We have to find this. This is what ultimately it boils down to, finding out X. But then how much necessary is this, is the fact that the numbers are all real numbers here. Yeah? For example, if you go to a power engineer, yeah, she will swear by, complex numbers only. Yeah, to her, these equations would make sense only if they're complex numbers, because they are phasors. I mean, if you are doing some sort of AC analysis, then you have no way out but to consider only complex numbers. If you go to a person who is doing cryptography, to her, this A, B, X, all these things may even come only from 0 and 1. To a number theorist, this A, B, X, all of them may be just positive, negative integers. Yeah. So then the question is, all these things that we have learned of row reduced echelon form and reading off of solutions, parametric, writing them down as in a parametric form, all of this, are they applicable in all the scenarios? Complex numbers, uh, binary 0, 1, integers, are they applicable everywhere? Well, most certainly it's going to be applicable for complex numbers. It's going to be applicable to 0, 1, as we'll see soon, but it will not be applicable to integers. Now, why is that? Yeah. So how do we know when it's going to be applicable and when it is not going to be applicable? The answer lies in the fact that when we are doing, so listen carefully, this is important. When we are doing this row reduced echelon form, the elementary row operations that we were doing, those elementary row operations were all of them involved things like, listen carefully, multiplying a row by a non-zero scalar, non-zero real number, and replacing a row by that row plus a constant time times another row. And then permutation is there. But permutation doesn't depend on the type of the numbers. It's always applicable, right? Here, the purpose was to create this one, the leading one, and then create the zeros in the columns that contain the leading one. That actually led to that row reduced echelon form, isn't it? Now, how did we create this one, the leading one? See, creating leading one is absolutely essential, because only when you create a leading one, only then can you use that one to create zeros in that leading one, to get those dependent variables, to fish out the dependent variables. But how did we get this one? Remember, we needed to divide by some number. And of course, when I do multiplication by a scalar, then addition and subtraction. So that means essentially, I must be able to carry out in these numbers, I must be able to carry out these four basic arithmetic operations, namely addition, subtraction, multiplication, and division, right? So then, in a nutshell, you can obtain this row reduced echelon form only when the numbers that you are dealing with allows you to do addition, subtraction, multiplication, and division. Yeah. And the abstract mathematical idea that tells us when a set allows these four operations is the so-called idea of a field, right? So let me just define what a field is. We'll see this abstract idea now. So we'll see this first level of abstraction, the idea of a field. What we mean by the field. So the definition goes like this. So let F, this is the standard notation for field, let F be a set with two operations plus and product, such that the following hold. Number one, so what we mean by these, okay, number one, what we mean by this plus and dot, for all, this symbol means for all, kind of rotated A. for all alpha, beta in the set. That means for all elements from the set, alpha plus beta, that is this operation of addition, the one that we call addition, is also an element in the field. In that case, it is said in words that the set F is closed under addition, right? This addition must satisfy certain properties. It must be commutative. So for all alpha comma beta in the field, alpha plus beta is equal to beta plus alpha. In words, this says addition is commutative. Number 3, for all alpha, beta, gamma in F, alpha plus beta plus gamma is equal to alpha plus beta plus gamma. In words, this means addition is associative. Okay. Then number 4, there exists an element called 0 in F such that for all alpha in F, 0 plus alpha is equal to alpha plus 0 is equal to alpha. Yeah? This 0 in F is called the, so this actually is unique. Although you don't need to assume this here, you can actually prove it, but let's just keep it this way. This is called the additive identity in F. Okay. Number 5, for all alpha in F, there exists a beta in F, although this also is unique, but we don't need this here. You can prove uniqueness. For all alpha in F, there exists a beta in F such that alpha plus beta equals beta plus alpha equals 0 in the field. Beta is called an additive inverse of alpha. Then number 6 is for all alpha beta in F, alpha times beta is in F. This is called F is closed under multiplication. Number 7, for all alpha beta in F, alpha times beta equals beta times alpha. That is, multiplication is commutative. Number 8, you can guess, for all alpha, beta, gamma in F, alpha, beta, gamma is the same as alpha, beta, gamma. This is written as multiplication is associative. Number 9, there exists a unique 1 in F such that for all alpha in F, 1 times alpha equals alpha times 1 equals alpha. 1 is called the multiplicative identity of the field F. And finally, I'm sorry, there is one more. Number 10 is for all alpha in F minus 0 minus the additive identity. So all alphas which are non-zero in F, there exists beta in F such that alpha beta equals beta alpha equals the 1. Beta is called a multiplicative inverse of alpha. And then finally, we have two operations. We have to say how these two operations are related with each other. So for all alpha, beta, gamma in F, alpha plus beta gamma is equal to alpha gamma plus beta gamma. In words, this means multiplication distributes over addition. Okay, so these 11 properties, when the set F satisfies, let F be a set with two operations plus and dot such that the following hold. So there are these 11 properties that these two operations satisfy. Then if the set, actually the notation is F plus and dot so that the operations also are clarified, then this is called a field. When it's clear from the context, we'll just write F. When the operations are clear from the context, we write just F instead of F plus and dot. Yeah, so this is how we define a field. So essentially that field means that all four operations are allowed. Yeah, why? It may be hidden in these 11 properties, but let me just clarify why this is so. So a closed under addition and multiplication is understandable. Existence of 0 is there, and then the moment I say additive identity, you see alpha plus beta equals 0. So that means we can define beta to be equal to minus alpha. And when you have minus alpha, that means somebody gives me an alpha and a gamma. I can do alpha plus gamma as well as I can do gamma minus alpha. Gamma plus alpha is allowed, gamma minus alpha is also allowed, because gamma minus alpha is nothing but gamma plus minus alpha, which happens to be the additive inverse of a number. Similarly, every non-zero number can be inverted because of the multiplicative identity. Because if there is an alpha, there will be a beta such that alpha beta is equal to 1. So therefore, that beta can be defined as alpha inverse. But remember that this has to be true for all non-zero guys, not for zero. So let us see some examples and things will be much clearer. So example of a field, of course, you can check very easily that the set of real numbers is a field, no doubt. You can check that all these properties are satisfied. I mean, these are so kind of, we are so used to this thing that we don't even go, don't even feel like stop and check that it satisfies these properties of a field. But you can go ahead and check that all these properties are satisfied by real numbers. Okay. You can also check, and I'm sure you already know this, C, the set of all complex numbers, is also a field. Do you know anything else? Well, of course, I'm sure you do. Q, namely the set of rational numbers, is a field. Now, what is rational numbers? Rational numbers, that means a typical element in Q looks like so. Say X must be a ratio of P by Q, where P and Q are positive or negative integers. So these are rational numbers. The idea of rational numbers is very, what should I say, very funny. But you see, we may kind of feel awkward to deal with real numbers, complex numbers. I mean, real numbers come very naturally to us because we always think that, okay, we have been seeing these real numbers, they are real numbers, right? What could go wrong with them? But you see, real numbers are also as imaginary as the complex numbers. They are all something that we have constructed for our benefit. And there is a famous saying by a great mathematician called G.H. Hardy. I mean, the guy who was mentor as in he invited Srinivas Ramanujan to England and to study higher mathematics. Yeah, so G.H. Hardy had made this comment once that God created integers, everything else is created by man. By man, of course, he means human beings. That means these are constructions that we have done, human beings have done. Naturally, what comes is only integers. In fact, that is also not completely true, completely correct. What is meant here is that you have to take something like given axioms, and from there you have to construct the rest. So what can be taken for given, the existence of which set can be taken for granted, is the set of all natural numbers that one can define through axioms. They are called Peano axioms. So Peano axioms give us Italian mathematician Giuseppe Peano. Peano axioms imply existence of natural numbers that is starting from 0, 1, 2, 3, 4, one can define. Yeah, it's defined. I mean, you don't have to think, okay, do they exist really? Do they? How can I see them? Is this set really existing? All those questions are immaterial because axiom says that they exist. So we have to start from there. Yeah. So natural numbers are there. From these natural numbers, one can construct. So human beings have constructed. So the H factor, the human being factor, has constructed from here positive and negative numbers, negative whole numbers, positive whole numbers. From there, I construct negative whole numbers that gives me integers. From this, once again, the human factor would give us the take ratios and form rational numbers. From there, do something like, once again, human factor, something called Cauchy completion that gives us real numbers. And from real numbers, do this algebraic construction of attaching the root of square root of -1. And that gives us the celebrated complex numbers. So that is how they are created. All of them are man-made. I mean, in the sense that humans have created. They don't exist naturally. By definition, what exists is the set of integers. That apart, the idea is that these numbers are, these sets are all of them fields because they satisfy all those 11 points that I have listed out for a field, right? Now, here is the question, are they all? Now, once we have these fields, before we come to the question, come to the answer of this question that whether they are all or not, but once I have these fields, you see, say F is a field. F is an arbitrary abstract field. Now, if I look for AX equal to B, where A is now an M cross N matrix with entries coming from F, B is a vector in F of size M, so we call it an M tuple. I'm using the word for the first time, but I'll be using it pretty frequently now from this point onwards. And X is from Fn, so it's an N tuple. That means it's of the form x1 dot 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 up to xn. So this is unknown. Because the field allows me to do addition, subtraction, division, and multiplication, I can see that I can solve for Ax equal to B by following those row operations that we have seen for the last few lectures. All of them will go through. So doesn't matter if it's rational number, we can do it. If it is real numbers, of course we can do it. If it is complex numbers, once again we can do it. What is even more surprising is that there are even more, even other kinds of fields, yeah, over which I can do these things. For example, okay, what is not a field? Let me tell you first what is not a field. Set of integers, set of positive integers. Is it a field? No, it's not a field. There is no additive inverse. So I take 1. Additive inverse of that we know, -1. But -1 is not there in this set. So it's not a field. Z, is it a field? No, it is not. Although it will have additive inverses, but it may or may not have multiplicative inverses. So here, if I take 2, so 2 is an integer. What is its multiplicative inverse? Half. Half is not there in this set. Neither is 1/3, 1/4, 1/5, and so on. Only 1 and -1 have their inverses here, multiplicative inverses. So therefore, Z is not a field. So therefore, if somebody gives you an equation of this kind, let's say 2x1 plus 3x2 equals 4 and 5x1 plus 6x2 equals 1, and asks you to give solutions x1, x2 as integers, you have to say that I don't know how to do this, because those row reduced echelon form kind of things is not going to work out here, because here they are integers. I cannot do all the operations and convert these equations to row reduced echelon form when I'm dealing with just integers. So if you're looking for only integer solutions, then the techniques learned so far are all of them inadequate. We need to do something else. We need to do something more different, right? So these are the cases where you cannot do what you have, cannot carry out what we have learned. Yeah. But let's not look into such negative things as of now. Let us look at some positive things. Let us see when we can do these things. Yeah, what sort of other sets where we can do this? In other words, what other fields would be there? So all these examples that we've seen so far kind of indicates as if fields are all these sort of things like rational numbers, infinitely many rational numbers are there, or real numbers, infinitely many real numbers are there, complex numbers, infinitely many complex numbers. Sort of indicates that a field should necessarily have infinitely many elements. Not true. A field can have finitely many elements also. Example, well, look at this one. So first example is what we call F2. F2 by definition is Z, the set of all integers, modulo 2. So what is modulo 2? Well, this by definition is collection of 0 and 1. Yeah. And what operations are we doing here? So let me first define what is Z modulo n. Yeah. So let me define Z modulo n. I'm going to define this addition and multiplication operation modulo n. So first, addition modulo n. What is that? So suppose I have two numbers A and B. So A, B, this is A plus B modulo n. What does this mean? This is, I'm doing A plus B. So this by definition is divide A plus B by n and write the, or let's say, and take the remainder. That is what we mean by A plus B modulo n. Yeah. A product B modulo n is AB modulo n. This is once again divide AB, that is product AB, by n and take the remainder. This is how the modulo operations are defined. So the set, so all possible remainders is the set when we say Z modulo n, and then the operations are defined like that. So now tell me, if I do Z modulo n, that set will contain what elements? What sort of remainders do we expect? Of course, the remainders can only be 0, 1, 2, 3 up to n minus 1. These are all possible remainders. Right? Remainders have to be necessarily smaller than that number, assuming n is a positive integer. Right? Similarly, so in this case, the way we are defining now F2, F2 by definition is Z modulo n. So as set, it will contain, oh sorry, Z modulo, F2 is Z modulo 2. Did I write 2? Yeah. So Z modulo 2. So this by definition will contain then 0 and 1. 2 minus 1 is 1, 0 and 1. What are the operations? Well, 0 plus 0 will be 0. 0 plus 1 will be 1, because 1 divided by 2 gives me remainder 1. Then 1 plus 0 is also 1. Then 1 plus 1 is equal to 2. But 2 when I divide by 2, so this is 2 modulo 2, but 2 modulo 2 is 0. I can write this up in the form of a table. So I have two elements, 0 and 1. Here also 0 and 1. So I'm defining the addition process. 0, 0 gives me 0, 0, 1 gives me 1, 1, 0 gives me 1, and 1, 1 gives me 0. right? Similarly, I can define product. So 0 times 0 is 0, 0 times 1 is 0, 1 times 0 is 0, 1 times 1 is 1, and 1 modulo 1 is 1. So therefore, I get the multiplication table also. I have 0, 1, 0, 1, multiplication, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 1. Yeah, and now you see, under these two operations, this indeed satisfies all the properties of a field. Seems surprising, but that is true. It satisfies all the properties of a field. So close under addition, yeah, because 0 plus 0 is 0, there, 0 plus 1 is 1, there, 1 plus 0 is 1, there, 1 plus 1 is 0, there. So addition is there. Addition is commutative, of course it is commutative. Addition is associative, of course it is associative, because all these are, the addition actually coming from addition in integers, and they are associative and commutative, so they also will satisfy same properties here. Is okay, additive identity 0. Yes, additive identity is there 0, and it indeed is true that 0 plus 1 is equal to 1 plus 0 is equal to 1 is equal to 1, right? Now additive inverse, well, 1, what is additive inverse of 1? What is additive inverse of 0? 0, of course. What is additive inverse of 1? 1 again, because 1 plus 1 is 0. 1 is its own additive inverse. Now coming on to multiplication, commutative, associative, fine. Then multiplicative identity 1, yes, 1 is there, right? And 1 times 0 is 0, fine. Multiplicative identity is there, multiplicative inverse, yes, 0, the only non-zero element is 1, and 1's multiplicative inverse is itself. So this indeed is a field, although trivial, but this is a field. You can actually go ahead and show that F3 also is a field. F3 defined as Z modulo 3, which contains 0, 1, 2, these three elements, and the addition is addition modulo 3, and multiplication is multiplication modulo 3. This is a field. F3 under this is a field. These fields are they are fascinating. They have all sorts of weird properties. Yeah, like for example, over this field of, this is called binary field. Yeah, by the way, F2, also called a Galois field, named after a great mathematician called Galois. I'll tell you the story of Galois some other time. Very fascinating story. So over F2, like, x square plus 1, we know that this doesn't factorize over R, right? This is root of -1. But you see, over the binary field, if you put over the binary field, this has a root in F2. Yeah, indeed. Like for example, it will factorize. Say I have x plus 1 and x plus 1 like this. If I do this product, I get x squared plus x plus x plus 1, right? So this is x squared plus 2x plus 1. But you see, 2 modulo 2 is 0. So 2x is actually 0x. So this is actually x squared plus 1. So this is how it factorizes here. So all sorts of weird things can happen, but true. So this you'll take as to show that F3 is a field, you'll take it as an immediate attention exercise problem. I will list out some other immediate attention problems in a short while. Before that, let me give you a challenging problem. So let me introduce this idea of a challenging problem for this course. I will often throw such kind of difficult problems, which if you solve, you don't get any credit for it, but you get a material benefit out of it, in the sense that if you properly solve a challenging problem and submit a solution, and if it is correct, then you stand a chance to win a book. Yeah, not some academic book, maybe some novel, or maybe a graphic novel, or maybe some popular science book, right? So here comes your first challenging problem. Challenging problem number 1. Construct a field, yeah, if such that it contains Q properly as a subfield. By the way, I haven't mentioned what is a subfield. Subfield means that it's a subset of a field, which is a field in itself, but it also has to have the same addition and multiplication, not some different idea of addition and multiplication. Yeah, so like for example here, 0, 1, the set 0, 1 with addition modulo 2 and multiplication modulo 2 is a field, but it cannot be called a subfield of Q in rational numbers or subfield of real numbers, because rational numbers, real numbers, they have different definition of addition than the addition modulo 2 that we have for F2. So therefore F2 is not a subfield of Q, neither is it a subfield of R. But Q is a subfield of R, or R is a subfield of C. You see, because they have the same addition and multiplication operations, right? So that is how one defines subfield. But now here you have to construct a subfield, construct a field F such that Q is a proper subfield, and F itself is a proper subfield of R. Can you do that? If you can do it, then I give you this problem that together with that, you also please construct Q, construct a family of fields F1, F2, dot, 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 such that Q subfield of F1, subfield of F2, finally subfield of R. Do this. Yeah. Also construct, because it's a challenging problem, you have to solve all this. Also construct a field F such that Q F C, but F is not a subfield of R. Do that. Okay, this is your challenging problem. Now let me describe the immediate attention problems. The first one is easy. I mean, the one that I have just described, that describe the do it this way so that it's clear. So write down the multiplication and addition table for F3. That is immediate attention problem number 2, problem number 1. Problem number 2 is over F3, solve this linear system of equations. Immediate attention problem number 3 is give an example of a matrix A over the binary field such that A is invertible over R, but it is not invertible over F2. Then give an example of a quadratic polynomial with coefficients in F2 that does not factorize over F2x. That is a polynomial that does not factorize. Yeah, kind of an irreducible quadratic polynomial. Then, very interesting, Fn, that is Z modulo n, is a field. Prove that this is a field if and only if n is a prime number. And then I will give you some homework problems. It has become homework 2, but homework 1. Yeah, this is a homework 1 problem. And then homework number 2 is construct a field that has 4 elements. Draw up the addition and multiplication table. Yeah, 4 elements. Think about it. Okay, this is where we call it an N for module number 1. Let us meet for module number 2. Okay, till then, bye-bye.